Guys, like we did yesterday in lab when we collected our data and you guys performed a couple titrations, did you actually feel like a scientist for once? All right, maybe, maybe not.
Yeah.
All right. It's more in-depth than other labs that we've done this year. That's why I like it. It's one of my favorite things that I do every year. Guys, so again, like we said, titrations, they're used to find the unknown concentration of either an acid or base, where you will titrate, meaning you're adding in a certain amount of volume of your known concentration of a solution. So if you're looking for an unknown acid, you're going to titrate with the base. If you're looking for an unknown base, you're going to titrate or add in the acid. Okay? What's the most important step in a titration? Otherwise, you won't know when to stop. Yeah, the indicator, right? Because if you don't have an indicator that changes color, it's going to stay clear. You're just going to keep going and going and going and going like the Energizer Bunny until you run out. Okay? So the indicator is the most important part. Why? Because that shows what we call an endpoint. All right? An endpoint, guys, is not the same thing as what was shown here on these graphs with that equivalence point. So, guys, within a titration, the whole purpose is we're trying to figure out the balance between what two ions? Hydrogen and hydroxide, okay? And that's exactly what these graphs show. So the one on the left here is showing where we have a titration curve of strong acid with a strong base. In this class, we're only going to worry about strong acid and strong base neutralization. We're not going to worry about if you have a weak acid and a strong base or a strong acid and a weak base. That's something more for AP Chem. Guys, the equivalence point, that's what we're looking for because what does equivalence sound like? Equal. Equal what, do you think?
Concentration.
Concentrations of what?
Acid base.
Which means what, though?
Hydrogen.
Ions. It's all about those ions, guys. So we're trying to get to the point where the hydrogen ion concentration equals the hydroxide ion concentration. At that point, that's when we can use that formula, MaVa equals MbVb. Okay? Because your two ions are equal. Now, the endpoint, that's when you go a little bit past that. So yesterday we used phenolphthalein as our indicator. When it got pink, that was what we called the endpoint, when we're done with the titration. That's not necessarily the same thing as the equivalence point. What color were you really looking for, guys, with the titration? Barely pink, right? Because if you go past it to the endpoint, you're past the equivalence point where those two ions are equal. And notice how steep of a curve this is, guys. With your volume, if you add even just a hair, one drop, you can immediately go from like a pH of, say, 3 all the way up to a pH of 12. It's a very, very fine line. That's why if you weren't sure if it was, maybe it was slightly pink, I said, hey, record the volume down. If you had one more drop, you know you've jumped up to the base part of it because you've gone just a little bit past this equilibrium here, all right, where they are equal. So that's what we're trying to get to. So when we go to do our math, we're doing it based on the equivalence point in our reaction. And that's where knowing the ratio between them is. So you can see, like, if you have weak acids and strong acids, guys, it shifts it a little bit so it doesn't look as the same. We're not going to worry about weak acids and bases here. We're looking at, like, just the nice, long, big curves with a big pH range. And that's what we did yesterday. All right. So let's jump in. Here we go. With our formula, guys, we're going to use it again. You don't have to memorize this. This is on table T. It's toward the bottom. All right.
So the acid gives you 1 hydrogen ion.
Right. So monoprotic, guys, is 1. How we say that scientifically is ionizable proton. So just 1 H plus. Diprotic would then be 2 ionizable protons. So you'd have 2 H plus, and triprotic would be, right, okay, you get the gist of it. Now, what's monohydroxy? Not hydrogen ion, what'd you say? That's, yeah, guys, that's just the same way of saying, hey, we have a base. It's monohydroxy, meaning you have 1 hydroxide that it's going to produce, or dihydroxy with 2. Okay? It's the same idea as monoprotic, diprotic, and stuff, but we're looking at, hey, we have a base there instead of an acid. So we have 1 sort of ionizable hydroxide ion. So just OH minus. And this would be 2 ionizable hydroxide. So 2 OH minus. Okay? So then I'm going to just kind of clarify this. This right here, guys, means you have an acid or to look at, and this is going to be your base. That's what hydroxy means. We will worry about them if it's mono, di, or tri at the end of the math problem, guys. That's going to be the last step we're going to take into account. So this is kind of on the flip side of those pH calculations. We had to look at mono, di, or tri beforehand and multiply the concentration by however many ions we had. Here we're going to wait until the very end calculation. Then we will multiply by however many we have. If it's mono, it is what it is. But if it's di or tri, we got to multiply by 2 or 3 respectively. All right, so word problem, guys. Like most of our problems in this class are word problems. And just think, in a couple months on that Regents exam, it's you, your brain, a calculator that's been reset, and a reference packet. That's all the resources. You cannot ask any questions of me on what do I do, how do I do this. You've got to figure out what formula you need to use. Okay? This is why all year long I've tried to train you to start pulling out that important information. So here we go. It says, in a titration, 27.4 mils of a standard solution of barium hydroxide is added to 20 mils of hydrochloric acid. The concentration of the barium hydroxide is 0.0154 molar. What is the molarity of the HCl? Lots of information. Can we just randomly write things down here? No, right? Because numbers aren't just the only important thing. It's what they refer to that's more important, even more important than just the numbers. So start looking at the numbers, guys. 27.4 mils. What am I going to label that as? What's my variable going to be for that? MA. Is that? What's M stand for? Capital M means molarity. So is that a molarity? Yeah. Why is it B, Jill? How do you know it's VB? How do you know that how do you know barium hydroxide is a base? OH, right? So basic ideas here, guys, are basic acid-base theory. Don't overthink it. We know that barium hydroxide is a base because it's got hydroxide there. So that's our volume of the base, 27.4 milliliters.
But we have to convert milliliters from molarity.
Hey, we can do that. That's a good strategy, right? Just so if we need it in liters, we already have it. So if we convert that right away, that's going to be what? 0.0274 liters. Okay, so since we have molarity there, it's a good habit if we need to have liters. What else am I given? It says is added to. Yeah, we have VA, which is 20.0 mils. Okay, again, how do I know that HCl is an acid? It's got the H. It's also one of those you have to have memorized for your test. Okay, there's strong acids and strong bases. Convert that as well, 0.0200 liters. Why am I keeping these zeros here, guys, at the end? Why am I not just writing it as 0.02? Sig figs. Sig figs will matter. All right, so we've got our 2 volumes. What else am I given?
Molarity of the base.
All right, so we've got molarity of the base, which equals 0.0154 molar. So we are looking for the molarity of our acid. Okay? Now, how this differs, guys, from the problems we've been doing with pH. pH, if we had a subscript, we multiplied the concentration at the beginning. We're going to wait to do that at the very, very end. All right? We'll take that into account. So, we've got VA equals VB. Very easy math, guys. We've done this on a couple different occasions, this same mathematical formula. Boyle's law and dilutions. All right? Solve for your missing piece. MA. Like I said, it's going to take me a while to get used to writing all these variables out the way that is. I've done it differently. MB, guys, we've got 0.0154 molar multiplied by our volume of our base, 0.02.
We're not looking for volume.
Oh, I meant to write an M. Like I said. I'm glad you guys called me on it sooner than later. Like, usually you just let me go until I get done and then tell me. All right. You guys are getting more gutsy. I like it. All right. Liters divided by M. No, it's not MA. Oh, my gosh. It's a Friday.
Just scrap the whole thing. Go home.
Just scrap the whole thing. If only we could. VA. That's what we're looking for. That's what we're looking for. That's what we need to divide by. Oh, my goodness. 0.0200 liters. Liters are going to be gone. All right. So go ahead and do the math, guys. 0.0154 times 0.0274 divided by 0.0200. Plug it in. What's the molarity of this value, Ma, that we got? 0.0211 molar. Now, we have omitted, guys, one key piece up until this point. All right? And at the end is where you're going to look for this. Take a look at our base, barium hydroxide. What do you notice about it? Is that a monohydroxy base or is that a dihydroxy base? It's a dihydroxy base, meaning there are twice as many hydroxide ions as hydrogen ions here. We've got to double the molarity here, guys, at the end. So we save it until the end. So really we're going to multiply this by 2 because we have 2 or twice as many hydroxides, which means if we're trying to neutralize it, the molarity of our acid has to be twice as strong. Okay, because it's got twice as many hydroxide ions to balance out. So really our molarity of our acid turns out to be what? Absolutely. Here we go. 25 mils of 0.2 molar. What's H2SO4?
An acid. Boom.
Well, okay, what acid? I'm asking the name of it.
Sulfuric acid.
You're right, it is an acid. I like that you were very confident in that. It's sulfuric acid. All right, so let's just jot that stuff down. We've got VA equals 20. Now, one thing I wanted to point out over here, guys, does it really matter with this formula if we convert these to liters or leave them as milliliters? No. Okay? Because we're not like using, it's just like our dilution formula. You don't have to convert that there like it is with our molarity formula where it's moles per liter. Since we have the same volume unit on both, it's not going to affect our results. So you can convert it if you want to, especially if you want to just keep it consistent, always doing that. That's fine. All right, so we really have, if we're going to convert it, 0.025 liters, and our molarity is 0.20 molar. All right, to neutralize, and another reason, folks, why we double that at the end, like we showed before, is because this is a neutralization reaction. All right, so when you neutralize it, you're getting to that equivalence point. So that's why you just take into account the number of ions at the end. So our volume of our base equals 0.037 liters. We're looking for the molarity of that base. So I need to get molarity of the base by itself. My molarity of my acid is 0.20 multiplied by 0.025 liters divided by 0.037 liters. Liters will cancel out. 0.2 times 0.025 divided by 0.037. Go ahead and do the math. Do it on your own. Don't wait for somebody else. Practice it. What's that? 0.27. 0.270. Sig figs would actually just be 2, but all right, 0.27 molar. Now, like Tony said a couple minutes ago, guys, he said, "Would we have to double it?" Well, take a look. There's one other piece that I kind of forgot to mention. All right, and it worked out with our last problem. It's okay. Take a look here, guys. HCl has 1, right? So it's a monoprotic. Our base was a dihydroxy. So since it was a different ratio, that's why we multiplied by it, which is exactly what we're going to do here. Our acid is a diprotic. Our base is a monohydroxy. So we have to double it. What if, let's just say for a hypothetical, that this wasn't NaOH, that this was BaOH2. Why?
Because there's 2 of each.
Right. Guys, if they're both, like if your acid is diprotic and your base is dihydroxy, it's the same ratio. The ratio is still 1, so you don't have to multiply it there because they each have 2 ionizable ions. Okay? I don't anticipate or I don't think on your Regents exam they would give you one where you have a diprotic and a dihydroxy. You're either going to have a monoprotic and monohydroxy or a diprotic and a 2 and 1 or 1 and 1. Okay, I don't think you're going to have where they're both 2 and 2. Multiply by 2. All right, so it's going to be 0.54.
It's already multiplied.
No, we didn't.
Yeah, it was.
Yeah.
Oh, you gave me the final answer?
Yes.
Oh, well, what was it without it being multiplied by 2?
0.135.
All right, that's what, because I just want to show that. 0.135, when you do that math right there, multiplied by 2, 0.27 molar is what it would be. All right, I got you. Now I'm with you. Volume of our base is 32 milliliters. Is added to volume of our acid, 10.0 mils. If the molarity of the barium hydroxide, the molarity of our base is 0.20 molar, we're looking for the molarity of our acid. MaVa equals MbVb. Divide by Va. All right, molarity, 0.20 multiplied by our volume of the base, 32 milliliters, divided by 10.0. Now, this math right here, what's the answer to this? 0.2 times 32?
0.64.
All right. Point what?
0.64.
This is?
Yeah, that's what I got.
All right. 0.64, and that is going to be the molarity there. What else do we have to do with it?
Double it.
Right. Again, barium hydroxide, guys, was 2. Nitric acid's formed this HNO3, so it's a 2-to-1 ratio. Yep, multiply it by 2. And so the molarity of our acid is 1.28 molar. Easy? Not too bad, right? So,